Welcome, dear learners. We are studying quantum chemistry, and in this module, we are discussing approximation methods. Approximation methods in quantum chemistry. The contents of this presentation include approximation methods, variation method, variation theorem, illustration of variation method, linear variation functions, and secular determinants. First of all, approximation methods. Schrödinger wave equation cannot be solved exactly for any atom or molecule more complicated than hydrogen atom. This means we can solve Schrödinger wave equation for hydrogen atom, but it is difficult for helium atom, which is a 2-electron system. And with increased number of electrons, the complexity as well as the ease of getting solution will be more difficult. This complexity, this difficulty in solving Schrödinger equation is mainly because of the repulsion energy terms of potential energy of such systems. And this potential energy, this repulsion parameters cannot be handled mathematically with analytical accuracy. So, this potential energy parameters arise due to various repulsions, create hurdles to get easy solutions of the Schrödinger wave equation for many electron systems. Approximation method, however, handle such systems numerically with good precision. Such a numerical method or approximation method has allowed to consider the complications brought about in multi-electron systems. The complexities that may appear in multi-electron systems include indistinguishability of electrons, spin associated with electron, interaction between orbital and spin magnetic moments. These kind of complexities can be addressed by different approximation methods, and such numerical approximation methods open up a easy way to solve the Schrödinger wave equation. Not exactly, but with good precision. Now, the approximation method have been developed for solving the Schrödinger equation to find out wave function and energy of the complex systems, many electron systems under consideration. There are two widely used approximation methods in quantum mechanics. The first and most popular method of approximation is the variation method. The second approximation method is the perturbation theory. So, under the heading approximation methods, we have to discuss these two type of approximation methods, their application, mathematical procedures, etc. And the present module give emphasis to the first approximation method, that is variation method. After giving a brief introduction to these two kind of approximation methods, we can directly go to details of the variation method. So, the first approximation method, that is variation method. All these points are very important as far as variation method is considered. Variation methods, in particular, the linear variation method are most widely used approximation methods in quantum chemistry. It is based on a theorem called variation theorem. So, variation method is based on variation theorem. This variation method provides a simple way to place an upper bound on ground state energy of any quantum system. Suppose there is a quantum system with the ground state energy, and by using this variation method, we can place one more energy level above the ground state level. That is, we can place an upper bound of energy by using variation method. This method of variation or variation method use trial wave functions in order to get a suitable wave function and a solution of Schrodinger wave equation. The second approximation method that is represented as, named as the perturbation theory. Perturbation theory is an approximation method that describes a complex quantum system in terms of a simpler system. But the simpler system has known solution, has exact solution. This simply means that perturbation theory find out the solution to one problem in terms of a problem which is already solved previously, For instance, suppose we are having a particle in one-dimensional box with a slanted bottom. Slanted bottom is a modified system where there is no direct solution in quantum chemistry. So, we are trying to explain or we are trying to solve the Schrodinger equation for particle in 1D box with a slanted bottom in terms of our particle in 1D box with a regular bottom. So, it means that we can solve complex systems by taking already solved similar simple systems. That is what we are doing in perturbation theory. In perturbation theory, there are two important types. Or perturbation theory can be categorized into two types. They are time-independent perturbation theory. This is put forward by Erwin Schrodinger. And the next one, time-dependent perturbation theory. That is proposed by Paul Dirac. So, the two categories of perturbation theory are time-independent perturbation theory by Erwin Schrodinger and time-dependent perturbation theory by Paul Dirac. Now, let us have a glimpse on the variation method. We are exclusively going to discuss the variation method. Our focus is on first most important approximation method, that is variation method. Consider the ground state of some arbitrary quantum mechanical system. The ground state wave function is marked as I0 and energy of the system is taken as E0. And psi0 and E0 satisfies the Schrodinger wave equation. H hat psi0 is equal to E0 psi0. Again, Hamiltonian is the operator, total energy operator corresponding to your system, your arbitrary system, where the ground state wave function is I0 and the ground state energy is E0. I mark that Schrodinger equation as equation number 1. Now, in order to illustrate the variation method procedure, we have to move numerically or mathematically. For that, I am taking this basic equation, this Schrodinger equation, and left multiply this equation with the psi0 star and integrate over all space. That is from minus infinity to plus infinity. So, I am going to multiply equation 1 left with the psi0 star, that is the complex conjugate of the ground state wave function psi0, that is psi0 star, and going to integrate over all space. Such that I will get, if I am multiplying LHS and RHS with the psi0 star, what we are getting? Multiply first and then integrate. So, integral psi0 star h hat psi 0 over space, so I put a d tau, is equal to energy can be taken as outside since it is a constant associated with a particular level. So, E0 into integral psi 0 star psi 0 d tau. From this, I can find out the ground state energy by simply rearranging this expression. That is, the ground state energy of the system E0 is given by integral psi 0 star h hat psi 0 d tau divided by integral psi 0 star psi 0 d tau. This equation represents the ground state energy associated with the quantum mechanical system. Now, consider a trial wave function, and the trial wave function is phi, which is an approximation. The trial wave function phi is an approximation. For us, let us have a system, a quantum mechanical system, that we wish to apply the variation principle. Let phi is a trial wave function, that is an arbitrary wave function, and the wave function, the trial wave function is always an approximation, a function constructed to emulate the value psi 0, the wave function of the ground state. The calculated energy would be like this. That is, the approximate wave function is phi. So, Hamiltonian phi is equal to E phi into phi. Hamiltonian phi is equal to E phi into phi. We can left multiply with the phi 0 star and integrate over space, what we have done in the previous slide. That is integral phi star Hamiltonian phi d tau equal to E phi into integral phi star phi d tau, phi star phi d tau. From this, we can find out E phi. That is, E phi is the energy associated with the system when we use a trial wave function. E phi will be equal to, this term goes to the denominator, such that E phi equal to integral phi star Hamiltonian phi d tau divided by phi star phi d tau, phi star phi d tau. This is E phi. What is meant by E phi? E phi is the energy of the quantum mechanical system where we are applying variation principle, and E phi is computed by using trial wave function phi with this expression. E phi is equal to integral phi star Hamiltonian phi d tau divided by integral phi star phi d tau. And here I wish to say something about the bra and ket representation. This integration, this term represented in the numerator can be simplified by this kind of representation. This is a bra and ket representation. Here we need not to put a complex conjugate, the integral sign, etc., etc. This integral phi 0 star part is marked as bra with the ket phi Hamiltonian phi d phi. D tau is not necessary here. So, this part can be represented like this. Here there is no, in the denominator there is no Hamiltonian operator. So, I am simply representing on line, on vertical line. So, this integral can also be represented like this. This about the value of E phi in integral representation and in bra and ket representation. We can use each and every representation conveniently. Now, the above integral, this kind of integral, that is the energy integral, the energy value used by or determined by the trial wave function, this integral or this ratio of this integral is more important, and it is termed as the variational integral. So, what is meant by variational integral? E phi equal to integral phi star Hamiltonian phi d tau divided by integral phi star phi d tau, or this term can be taken as the variational integral. Now we are moving on to variation theorem. Variation method is based on variation theorem. And this is the mathematical representation of the variation theorem. What is meant by E0? It is the ground state energy of the system. What is E phi? It is the approximate energy of the system. That is, energy of the system evaluated by using a trial wave function. So, variation theorem says that the approximation, the energy calculated by using variation principle, will always greater than or equal to E0. And this equality holds good if and only if we get to the real wave function. Instead of the trial wave function, if we go to the real wave function, then E phi will be equal to E0. Otherwise, if you are proceeding with a trial wave function other than original wave function, the calculated energy E phi must be greater than E0. So, in general, we can say E phi greater than or equal to E0. That is, calculated energy will be always upper bound to the ground state energy. So, calculated energy may be equal to ground state energy provided the trial wave function must be equal to original wave function psi 0. Variation theorem provides the basis of the variation method. It states that any trial wave function other than true function psi 0 would give an energy E phi that is higher than the true ground state energy of the system. That is, E phi greater than or equal to E0. And this equality, equal sign, is valid if and only if the trial wave function phi is equal to original wave function. So, if you are taking some approximation, if I got the trial wave function as the original wave function, then E phi will be equal to E0. That means E phi will be equal to E0. The equality holds good if and only if the selected trial wave function will be equal to original ground state wave function of the system. Otherwise, the calculated energy E phi will be greater than ground state energy of the system. This statement is called the variation theorem. It states that any trial wave function other than the true function psi 0 would give an energy E phi that is higher than the true energy E0. Now, the variational principle says that we can calculate an upper bound, means a high energy than E0, by using any trial wave function we wish. The closer the value of trial wave function to ground state wave function, in some sense, the more closer E phi, that is trial energy, with the ground state energy or original energy, which simply indicates that if trial wave function is closer to ground state wave function, trial energy will also be close to ground state energy. We can choose a trial wave function phi such that it depends upon some arbitrary parameters. That is, phi depends on some arbitrary parameters. The arbitrary parameters are denoted as alpha, beta, gamma, delta, etc. And such parameters are called variational parameters. So, what are variational parameters? Variational parameters are the parameters that depend the wave function, trial wave function phi, that govern trial wave function phi. So, phi can be represented as phi of alpha, beta, gamma, etc. The energy also will depend on these variational parameters alpha, beta and gamma. In that sense, we can write energy phi, that is the approximate energy, depends on alpha, beta, gamma, etc. will also greater than or equal to E0. So, instead of E phi, I put E phi of alpha, beta, gamma, etc. because the trial energy or energy calculated using the trial wave function also depends on variational parameters. Now, after getting this energy, we have to minimize this energy with respect to each of the variational parameters and thus approach the exact ground state energy is 0. So first we have to determine E phi or energy of the system by using a trial wave function. Then we have to minimize the E phi, the calculated energy. That minimization gives an approach that the minimized energy is more close to ground state energy is 0. This is the procedure we are generally adopting in the variation method. Now, we are going to illustrate the variation method using a common quantum mechanical problem. The variation method can be illustrated by considering the ground state of a harmonic oscillator. We already learned in previous modules about 1D harmonic oscillator, 3D harmonic oscillator, etc. Let us take a trial wave function of the present system. So, it should be noted that in order to illustrate or exemplify the variation method, we first must have a trial wave function. And the trial wave function is constructed based on some logic, and the energy calculated based on the trial wave function is termed as E phi. And E phi must always be greater than or equal to E0, that is variation principle. So here we are going to take harmonic oscillator as a problem to illustrate the variation method. Let us now take a trial wave function which is fixed as phi is equal to cos lambda x. This is for 1D SHO that execute simple harmonic oscillation along the x direction. And here the limit of x is from minus pi by 2 lambda to plus pi by 2 lambda. That is, x ranges from minus pi by 2 lambda to plus pi by 2 lambda. And this is taken as the trial wave function. And this is the range of x that appeared in the trial wave function. Here lambda is a parameter that I already mentioned. The wave function as well as energy depend on some parameter called the variational parameter. So, we are having 1D harmonic oscillator with us. I took a trial wave function that better describe the 1D SHO, and the trial wave function is phi is equal to cos lambda x, where lambda is the variational parameter, and the value of x ranges from minus pi by 2 lambda less than or equal less than x less than pi by 2 lambda. That means the value of x that appeared in this trial wave function ranges from minus pi by 2 lambda to plus pi by 2 lambda. And by using this trial wave function, we have to evaluate the energy of the system, then minimize the energy of the system, then compare that to minimize the energy with original energy. Then we will feel the worthfulness nature of the variation method. We can proceed. The Hamiltonian operator for a simple harmonic oscillator is already established. H hat for 1D SHO is equal to minus s cross square by 2 mu d square by ds square plus k by 2 x square plus k by 2 s square. Here k is a constant called force constant. S cross is equal to h by 2 pi known as Dirac. Mu is the reduced mass of the system. This is the Hamiltonian operator corresponds to 1D SHO that execute simple harmonic oscillation along x direction. That's why d square by dx square. If it execute SHO along y direction, simple harmonic oscillation along y direction, this d square by dy square will be the term, and this x should also be replaced by y. So we are considering 1D SHO along x-axis, and the Hamiltonian of the system is minus s cross square by 2 mu d square by ds square plus k by 2 x square. We already have the trial wave function phi is equal to cos lambda x, and we have already studied the variational integral. E phi is equal to integral phi star Hamiltonian phi d tau divided by phi star phi d tau, out of which we know Hamiltonian, this is the Hamiltonian, and we know phi, that is equal to cos lambda x. Phi is equal to phi star because there is no imaginary part, and hence substituting Hamiltonian and phi in this expression, we will get numerator part. This numerator part will be equal to integral minus pi by 2 lambda plus pi by 2 lambda cos lambda x minus s square by 2 mu d square by d square plus k by 2 square cos lambda x dx. On simplification, the numerator part, the encircled numerator part will be changed to pi s cross square lambda by 4 mu plus pi cube by 48 minus pi by 8 into k by lambda cube. Similarly, we can evaluate the denominator also. The denominator is integral phi star phi d2. The denominator will be equal to pi by 2 lambda. Thus, we get energy phi. Instead of energy phi, I am putting energy lambda since lambda is the variational parameter. Numerator by denominator, on simplification, I got s cross square by lambda square by 2 mu plus pi square by 24 minus 1 by 4 into k by lambda square. And this is the calculated energy. This calculated energy must be minimized with respect to variational parameter lambda. As a minimization condition, we have to take this dou E by dou lambda. First derivative of the calculated energy must be taken as 0. So, I have to differentiate this equation with respect to lambda, and the result must be equated to 0. From that equation, I will get the value of lambda. Then substitute that value of lambda back in this expression. So, whenever I have to minimize this, I will get the value of lambda from this expression, dou E by dou lambda equal to 0. So, we have to differentiate this with respect to lambda, equate the result to 0 to get the value of the variational parameter lambda. Again, this value, this calculated lambda value is substituted in the energy expression. Thus, we are getting the minimized energy. The minimized energy, E minimum will be equal to pi square by 3 minus 2 the whole raised to 1 by 2 into half s cross k by mu the whole raised to 1 by 2. After putting the constant values, we got the result as 1.14 half s cross. 1.14 s cross. 1.14 s cross. 1.14 s cross. This is 1.14 s cross omega. No half is there, 1.14 s cross. Compare with this value with the exact value. We already know about only simple harmonic oscillator. Its energy is already evaluated. Its ground state energy will be E0 is equal to half s cross omega. So, the present result is 1.14 s cross and the actual result is half s cross omega. This means that E lambda is equal to 1.14 s cross omega with the trial wave function cos lambda x. And actual energy E0 equal to half s cross omega means 0.5 s cross omega. And it is also clear that the calculated energy E lambda greater than E0. Also, there is an agreement between trial wave function and the ground state wave function. Now, we can graphically represent the wave functions. We calculated energy and there is an agreement between wave function also. The trial wave function and the original wave function are graphically shown here. The solid curve represents the trial wave function, that is phi is equal to cos lambda x, and this is the dotted curve which represents exact ground state wave function. And these two pictures mainly merges in many positions, and it is clear that the ground state wave function as well as trial wave function are in good agreement with each other. Now, we are going to discuss linear variation functions. In variation method, a trial wave function will be constructed with adjustable parameters so that it could be varied to improve the trial wave function. If a trial wave function phi is represented as a linear combination of some arbitrary functions, then phi is called a linear variation function. A linear variation function is a linear combination of n linearly independent functions, f1, f2, etc. up to f1. Simply, a trial wave function phi is a linear variation function. Then we can write phi is equal to summation n is equal to 1 to n Cn f1. Here Cn's are variational parameters and f1 are arbitrary known functions that at least satisfies the boundary conditions. A trial function that depends linearly on the variable parameters leads to a secular determinant. This can be illustrated by considering a linear variation function phi as phi is equal to n is equal to 1 to n Cn f1. Let n is equal to 2 such that this equation simplified into phi is equal to C1 f1 plus C2 f2. F1 and f2 are any two arbitrary functions. C1 and C2 are the variational parameters. Now, we have the variational integral E phi is equal to integral phi star Hamiltonian phi d tau divided by integral phi star phi d tau. Substitute the value of phi and evaluate the integral such that the numerator will be phi h hat phi d tau. Phi star is equal to phi since we are dealing with the real part, there is no imaginary number I. So phi is equal to phi star. There is no complex conjugate. On substituting the value of phi as C1 f1 plus C2 f2, you will get this integral. On final simplification, you are getting the numerator as C1 square integral f1 h hat f1 d tau, C1 C2 integral f1 h hat f2 d tau, C1 C2 integral f2 h hat f1 d tau plus C2 square integral f2 h hat f2 d tau. Now make some substitutions. Let hij is equal to integral fi h hat fj d tau, hij equal to hi since Hermitian. Moreover, we are getting the numerator of the variational integral as integral phi h hat phi d tau is equal to C1 square h double 1 plus 2 C1 C2 h12 plus C2 square h22. Similarly, integral phi square d tau, the denominator of the variational integral, can be simplified like this, where Sij and Sj are known as overlap integral, represented as integral fi fj d tau. On putting the values of hij and Sij, they are known as the Hamiltonian integral and the overlap integral. We are getting the final value of the variational integral as well as the energy of the system. The energy of the system is C1 C2 will be equal to numerator, that is C1 square h double 1 plus 2 C1 C2 h12 plus C2 square h22 divided by denominator, that is C1 square s11 plus 2 C1 C2 s12 plus s22. We are getting this energy. And as a further procedure, we have to minimize this energy with respect to each variational parameter, say C1 and C2. For that, I have to differentiate this energy with respect to C1 and equate it to 0 and evaluate the value of C1. Similarly, I have to differentiate this energy expression with respect to C2 and equate it to 0, then to evaluate to C2. Then the determined C1 and C2 must be substituted here to get the minimum energy associated with the system as a procedure in variation method. We can write this expression, we can cross multiply and this equation can be changed to this. Here we have to E is a function of variational parameter C1 and C2, differentiate to 2 with respect to C1 to get this expression. We have to minimize this with respect to C1, so dou E by dou C1 is 0, and on simplification we get an equation like this. Similarly, we have to differentiate 1 with respect to C2 and proceed accordingly and equate dou E by dou C2 to 0 to get this expression. So, we are getting two equations 4 and 5, and such equations can be represented like this. Equation 4 and 5 constitute a pair of linear algebraic equations in C1 and C2. According to principle of linear algebra, the essential condition for this equation to have a non-trivial solution is that the determinant of the coefficients of C1 and C2 should vanish. That is, the coefficients can be set out into the form of a determinant, and that determinant must vanish or that must be equal to 0. This is such a determinant. H11 minus ES11, H12 minus ES12, H12 minus ES12, H22 minus ES22. And this determinant is equal to 0. This relation is called, this full relation, equation number 6, is called the secular equation, and left hand side, this part is a determinant known as the secular determinant. The solution of which yield, on solving this secular determinant, we yield minimized energy of the system with respect to trial wave function. Hence, in this module, we mentioned about different approximation methods. We considered variation method in detail, and we illustrated it with the simple harmonic oscillator, and finally discussed linear variation principle. That's all about this module. Have a nice learning experience. Thank you.